Do you know modal analysis of a three-story building examines its dynamic behavior by identifying natural frequencies and mode shapes? In this study, structural vibrations are analyzed using ABAQUS to understand how the building responds to overall excitations, helping in optimizing design, ensuring stability, and assessing the building's overall structural integrity.
Hey friends, if you're new here, I am Dr. Jawed Qureshi, a senior lecturer at a London university. On this channel, we explore technical and human skills to help us lead more productive, happy, and examine life.
In this lecture, I will cover modal analysis of a three-story building in 3 dimensions, and I will compare this with lump mass approach using 2-dimensional structure, and we will see that if the frequencies obtained from 3D and 2D model, they compare well or not. This is a problem which has been taken from structural dynamics by Esfahani et al. The material is steel and the sections are structural hollow sections. The material properties are given and we are required to find out natural frequency and mode shapes. I will be using SI units in millimeter, where length is in millimeter, force is in newtons. As usual, I will be using these 9 steps to model the structure. Let us now start to model this structure. Remember that the dimensions 3 meter and 3 meter here, they are internal dimensions between the beams. If we count the center to center dimension, it will be 3.3 meters between these 2 beams. So in modeling, we'll be using 3.3 spacing between the beams. Let's see how we can model this problem. Remember, section size is 300 by 300 and it is 25 millimeter thick section. First step is part where we will create geometry. Start with ABAQUS. Go to parts first, say beam, 3-dimensional space, extrusion, and approximate size is 2000. Click continue. I will start with this rectangle. Lower left point is -150, -150. Upper right point will be 150, 150. And then I will create another rectangle, -125, -125. The upper right corner will be 125, 125. This will give me square hollow section, and you can check its dimension by simply clicking on dimensions. This is 300 and the internal dimension is 250, and the thickness is, if you have a look at vertical dimension, it is 25. It means that we have drawn the section properly. Simply cancel the procedure and give the length of the beam, which is 3000. Click OK. The beam has been created. Second step is property module, where we will define materials and assign cross sections. The next thing is to define the property. To go to materials, I will say steel, and first I will define the density. Density is 7850 E raised -9 kg per millimeter cube. That's why we have E raised -9. And elasticity 210,000. Poisson's ratio is 0.3. And then I will define the plastic properties as well. Although plastic properties are not needed because this is linear elastic analysis, so there is no need to define them, but as it is given, I will define that. 370 and plastic strain is 0. And for 460, you can assume it to be between 0.18 to 0.25. So I'm assuming the maximum 1.25. Click OK. The material has been defined. Next, I will define the section, solid section, homogeneous. Click continue, and material is a steel. Then I will assign this section. Go to beam, go to section assignment, choose the section, click done, and OK. Third step is assembly module, where we will assemble all parts. The next and most important module is assembly. It is a bit of a challenge to assemble this into 3-story building. So go to assembly. First, I will create the instances. To create instance, so first is the beam, and then I will create another beam over here in X direction. Because I cannot use this instance linear pattern in Z direction, so that's the reason I have to create 1 beam in this direction and 2 beams in X direction and 1 column. And that way I will be able to create the entire building. So first, let's create another instance. Auto offset from the first one. I want to rotate it into horizontal direction. Go to instance, go to rotate, choose it. The point of rotation, because I want to rotate it in horizontal direction, it will be rotating around the vertical axis. So give the coordinates for vertical axis. The beam has been rotated now. I want to translate this instance to the corner of this instance. So go to instance and translate, choose this one and translate this point to this point and click OK. Next, I want to draw another beam over here in this direction. So go to instance, create in the same way, and I want to rotate this. Choose this one and give the vertical axis and 90 degrees. The section has been rotated, and then corner of this point is going to be over here at this corner. So I will translate this beam, click done, and translate this end point to this point. The section has been translated, and then I will define two columns over here. Go to instance again, create, and I want to rotate it in vertical direction, so my dimension is going to be horizontal. My axis is going to be horizontal axis 90. The section has been defined. I will translate this instance to this position, choose the section and choose this point. Choose this point, section has been translated. And next I want a column over there. Go to instance again, create, and then rotate the instance, and axis is going to be horizontal 90 degrees. The instance has been defined. I want to move this instance at this position. Go to instance and translate, choose the instance, done. I want this point to be over here. The section has been translated. Now I will create linear patterns, and you will see that we cannot create linear pattern in Z direction. We can only create in X and Y direction. So go to instance and linear pattern. I will choose this instance, click OK, and in X-axis direction the dimensions are 3300, and I need two of the beams. In Y dimension the dimensions are 3000. In that way you can create these beams, and same is the case for these beams. So go to linear pattern and choose this beam. This can only go in vertical direction, so I will simply create offset of 3000, and I will create 3 of them, and then I will create a linear pattern for other beam as well. So go to linear pattern, this one in vertical direction only, and I need beams in with 3 meter spacing, and then I will create these columns. So go to instance, linear pattern, choose this column. In X direction I have to give 3300, otherwise it will not be in the position because the dimension between beams is 3.3 meters. In that way these columns have been created. The next would be to create a linear pattern for this column. So go to instance, linear pattern, and choose the column, and in X direction you will be having 3300, and in Y direction you will have 3 columns. In that way I have created this geometry. Fourth step is step module, where we define all analysis steps and parameters. Next part would be step. In a step, simply create a step, say frac, and it is linear perturbation, frequency, click OK, and I would like 10 mode shapes, click done. Fifth is interaction module, where we define contact interactions and constraints. The next step is interactions. In interactions, I will go to interactions and find contact pair. And here I will click on find contact pair, and whatever contact pairs have appeared, I will simply not surface to surface interaction. I would like tie constraint. So I want to tie the ends of the beams with columns. So now these surfaces have been tied. It means that in real practice, these are welded joints. Sixth is load module, where we define boundary conditions and loading. The next would be load. In loading, I will define the boundary conditions, and boundary conditions, I will define a fixed boundary condition at the base. So write down fix, displacement, symmetry in caster, click continue. And here I would like to choose the base of the entire structure. I'll choose this surface, press shift key, choose this surface again, keep shift key pressed, and choose this surface, and finally choose this surface. And I want to apply encaster, which means that the fixed support. The fixed support has been assigned to the model. Seventh is mesh module, where we define mesh size and element type. Once loading is assigned, then I'll go to mesh and I would like to mesh the part. Here simply I would like the element types. I want to use reduce integration element, brick elements. This is fine. I want to seed the part. It says 250. I will use 50 mesh. It will be fairly refined, and then I will mesh the part. And if you wanted to see assembly, entire assembly has been meshed now. Eighth is job module, which we use to run and monitor analysis. The next step is job. We'll simply say frac. And after this, I would like to set up the working directory and save the model. So set up working directory. And simply I will submit the job and monitor it. Some warnings are there because I said adjust the nodes, so probably ignore these warnings. It will take a while because the model is quite heavy. Ninth is visualization module used for viewing results. A clean solution, I will go to data file. First thing I want to note is the total mass, which is 15,543. Keep this thing in mind because when we are going to use the two-dimensional model, then you will need this value. The frequency, first frequency 225 and second is 0.227, 0.30, 0.45 and so on. Some of them are translational and some of them are rotational. First one is in Z direction and next one is in Z direction as well. And the third one is in X direction. You can view the results by simply going to monitor. Here you can have a look at the results. Here I want to superimpose the models and then I want to run the movie as well. You can see how they are deflecting, and if you like you can simply free up the edges, and that way you'll be able to see it clearly. This is the first mode, and you want to have a look at the second mode. This is the second one, then we have the third one, fourth, fifth. In that way we can model this structure in 3 dimensions. Now let us see that if lumped mass approach can predict the same mode shapes, certainly it's not going to predict the rotational ones. Let us now use lumped mass approach. In lumped mass approach, we assume that the entire mass of a structure is lumped at one point. It is necessary that the frames should be spaced at equal distance. Here, because we have 3-meter distance all the way through it, so that's why we can use this model. This lumped mass assumed that entire mass of 4 beams here and 4 columns here is lumped at one position. Now, how do we work out mass of 4 beams and 4 columns? Mass is equal to density into volume. First, we work out the area of the section, and then we have 8 beams and columns all together. We multiply it with the length, which is 3 meters, and then we multiply it with the density of the steel. We get mass as 5181 kgs. So for lumped mass approach, we have mass which is lumped. We will take one frame. For this, it is necessary that the frames should be equally spaced. If there are 10 frames along the line, they should be equally spaced. Otherwise, you can't use this technique. 3-dimensional is the most accurate one, but lumped mass approach is really quick one. In the numerical solution, it is faster. Also, you can use hand calculations up to 2 degrees of freedom. If it is 3 degrees of freedom, you will simply struggle to work it out. But for 2 degrees, yes, there are 2 masses, you can work it out fairly easily. So let us see how we can solve this problem in 2 dimensions. I will copy this model over and I will say 2D model. So I will go to 2D model and I will delete this part beam, and I will delete the section as well because our section is going to be different. I'll keep the material. One thing I forgot to do is that I didn't have to define density here because all the mass has been lumped over here. So there is no need to define density. So I will get rid of this density. Otherwise, what model will do that it will work out the mass 2 times. One time it will be using the density of the material and multiplying it with the sections, other time lumped one. So in lumped mass, we normally don't define density, or we reduce the density to a very small value. So plastic, I don't need it as well. So here I will get rid of it and then click OK. So go to parts. I will say 2D beam and deformable wire and 2000. And here simply I want to create 3 frames. So starting from here and then create another frame here and simply create the third one. And I want to define equal length constraint. So here equal length constraint, equal length, press shift key and hold these columns, equal length, press shift key and hold these 3 beams. Equal length has been assigned, and here I want to dimension this part as 3000 and I want to dimension this part as 3000 as well. In that way the part has been created. Then I will create a section. Go to section. Here I will choose beam section and steel 0.3, and here I will create a profile. A box profile. Width is 300, height is 300 as well, thickness is 25. Continue. Then I will assign that section to the entire frame. Assign this section. At this point I will assign the beam section orientations as well. So go to assign beam section orientation, choose the entire frame, click done and OK to confirm. I will go to assembly, and here instance I will create the entire geometry and then step. Delete the step and I will define another step that will be linear perturbation. It will be frequency, and here I want 10 mode shapes. Click OK. Step has been defined. Once a step has been defined, then I will go to interaction. Here first of all I will define the reference point. So reference point for mass 1, for mass 2, for mass 3. Then I will tie up that reference point. So go to constraint. I will delete the prior constraint when I tied 3D section. So I will delete all those constraints. So go to tie rigid body, click OK. Then tie constraint. First I will choose this beam and then reference point is the first one and adjust the point. It has been tied. Next constraint is again tie nodes. The second is flow and reference point is reference point 2. I will adjust it as well. And third one is the top one, tie nodes. Then I will put the mass, which is 5181 kg. Go to assembly, go to engineering features and inertia. Here inertia 1 is M1 and choose this point. M1 is 5181. Click OK and then define an M2 point mass. And then I'll go to load. At load I have the boundary conditions. I will say fix. Click OK. I'll choose these 2 points and encaster. In that way the boundary conditions have been defined. Note that I don't need any load because I'm working out the natural frequency. Then I'll go to mesh and simply element type at part level. Element type, choose the entire structure. Elements are quadratic. Continue. Then I will seed the part 50 seeds and simply I will mesh the part. Once the part has been meshed, then I will go to job and I will define another job for model 2. Simply I will say frac 2, submit it. This time it's going to be far quicker than earlier. The point I want you to note here is that the mass is same, 15,543. The one that is worked out by the software without applying any lump mass approach with the help of density, it is same as we used in lump mass approach. It means that the results are going to be similar as well. So the first modes are really rigid body modes. The one which I want to look over here is 0.22485, 0.22485, which is in X direction, and it is very similar to what we got from 3D model. If you want, you can have a look at results. I want to have a look at the third one. If you want, you can have a look at other modes as well. In that way, you can see that lump mass approach, it gives same results as you get from a three-dimensional model where the mass is not lumped. But certainly, three-dimensional model is going to give you the right behavior of the structure, because it will take into account the movement of sections in every direction, and you will get the rotational frequencies as well. Here, it's mainly translational frequencies in two-dimensional model. You can have a look at the lecture slides at tinyurl.com/jqureshi abacus.